Hello everyone, welcome to our video presentation for operating system assignment 2. We are group A6. Operating system is all about managing resources efficiently, and today we are going to show you how we solve the problems regarding concurrency and scheduling. Before we dive into the code, here is our roadmap for today. Please look at the content page. First, I will kick things off with task 1, focusing on the most basic synchronization primitive, the task and set instruction. Next, ZHONG will show you demo and explain why basic explaining is actually quite wasteful. Then, YILING will introduce task 2, where we build a smarter counting symbol with strict FIFO fairness to solve that waste problem. Finally, QILONG will wrap up with task 3, analyzing task scheduling strategies like the elevator algorithm. Okay, let's start with task 1A. In a multi-threaded world, the biggest enemy is a chaos. Two threads touching the same data at the same time. To stop this, we need a lock. Please focus on the code here on page 6. We implemented a function called test and set. Many people think locking just setting a variable to 1, but if you do that in normal code, it happens in steps and threads can crash into each other. So look at the line 28. This line and this function. This function is amazing, a magic, because it is a topic. Think of it like the grabbing a last piece of pizza on the table. You don't check if you here and then grab it. You do that in one single lightning fast motion, right? So this function sets a flag to true or busy and return the old value instantly. If returned false, congratulations, the lock is yours. But if you return the true, sorry, someone else held it and you must wait. Now, I would like to introduce to you all the technical detail. Look at this line. Why did we use this line? Why did we use this statement? You can take a guess, but I want to use an example to you for explanation. Please take a imagine. I write a note in a room and then lock the door without this cry command. And then the CPU may be lazy and lets the next person enter before note is fully visible. This command forces the system to play fair. It's guaranteed that when I get the lock, I see the absolute latest data written by a previous owner. It ensures safety and visibility. So we have a safe lock, but how do we use it? And then, is it efficient? We don't know. So next, the ZHONG will now demonstrate this task 1B.
Hi everyone, I'm ZHONG. Tianfeng gave us the lock tool. Now, I will show you how we use it in task 1B. Does the lock work? Yes. Look at the evidence on page 10. You say enter 32, then it works, then exit 32. Only after 32 exits does 3 to 1 enter. It is very polite, one by one. The final count is 15, which matches our expectation perfectly. 5 threads multiply 3 iteration, so mutual exclusion is verified. But it is efficient? Absolutely not. Let's look at the acquire function on page 13. Look at this while loop. This is what we are calling speeding. Imagine you need to use the bathroom, but it's occupied. Instead of wasting on the beach, you knock on the door every millisecond yelling, Are you done? Are you done? Now, how about now? This is called busy waiting. It's annoying, but it's burning energy. How bad is it? We did the math on page 17. We have 5 threads all in one convoke. The other 4 are just speeding. Let's calculate to an 18% CPU waste ratio and look at the real data on page 13. Total field toast is over 500,000. We clocked on the door 500,000 time for nothing. This is a occupy table for every short waste, but terrible for non-tasks. We need to waste you, and that is that YILING will introduce.
Hello, I am YILING. In task 2A, I implemented a counting semaphore with FIFO fairness to fix XIANGYU's knocking problem. You can think of this like a bank service counter, where all windows are full. You don't stand here yelling. You take a ticket number and you wait in the sleeping area. Let's look at the structure on page 26. This page shows us waiting room. We use an aesthetic queue to maintain strict FIFO order. Each waiting thread is represented by a waiter struct, which contains an aesthetic condition variable. This is the key mechanism that allows threads to sleep. Now, let's move to the wait function on 28. This is the most critical part. In the wait function, when value equals 0, meaning there are no permits left, the thread does no spin. Instead, it takes a ticket by checking the sequence number myWaiter arrow SEQ. Then the thread goes to sleep. At 9118, we wait on the condition variable of this waiter. This causes the thread to enter a blockade state. It consumes 0 CPU and remains completely silent until it is exactly woken up. Next, let's see how threads are woken up. This happens in the signal function on page 29. At 9140, we select the front of the wait queue. This means we always pick the oldest waiting thread. At line 159, we modify exactly one waiting thread using this condition variable. Only that specific thread is modified. Notify the comment do not incriminate value. The permanent is passed directly to waiting thread. This prevents any new threads from cutting in line. As a result, strict FIFO fairness is guaranteed.
Hi everyone, I'm QILONG. YILING claimed her code is fair. Now let me prove it with actual data from task 2B. Please look closely at the logs on page 25. We have two proofs here. Bounded concurrency. Look at the bottom summary. Max concurrent thread is CS equals to 3. This matches the requirement perfectly. FIFO proof. Watch the sequence. Thread 3 gets Q first with sequence equals to 1. Thread 5 gets Q second with sequence equals to 2. When a slot opened, the log says wait waiter sequence 1. Thread 3 Q first, so thread 3 enter first. This proves our system prevents starvation. Finally, for task 3, we analyze this scheduling. Imagine that this cat is elevator serving requests on different floors tracks. We compare 4 strategies using the data on page 42. FCFS. The chaotic elevator. It goes from floor 53 to 98, then all the way to 183, then back to 37. It travels 640 cylinders. It's fair but very slow. SSTF, the lazy elevator, it only goes to the closest floor. It travels only 236 cylinders. It's fast, but if you are far away, the elevator might never come for you. Starvation. Scan. The real elevator, it goes all the way up, then reverses. It travels 236 cylinders too. It balances speed and fairness. C-scan. The teleporting elevator, it goes up and then jump back to the start without stopping. It travels 382 cylinders. Why use it? Because it provides the most uniform wait time for all users. To wrap up our presentation, we started with the basic log in task 1 but found it wastefully. We solved it with a sleeping semaphore in task 2, then enforced static order. We applied these principles to disk scheduling in task 3. Recommend the C-scan for fair, multi-user system. This concludes Group A6's presentation. Thank you for watching.